Science Association. We run the science workshops for fees. Dr. Daniel Harris, I'll introduce more later because he's going to be our speaker tonight. A couple of things that I wanted to get across to you. Unfortunately, he's got this in presenter mode, and I'm not going to change that. In May, because we have, this is our last science workshop for this year. We will move them next year over to the Feast campus. But we continually, on second Tuesdays each month, have regular SABSA meetings here. And it's very gracious of Faith Lutheran to host us. In May, on the second Tuesday, we will have a series from the Institute of Creation Research called Made in His Image. Tremendous material about how a baby transfers from being in a water environment to a air-breathing environment in seconds. How the eye challenges evolution, how the motion of your body, how your body is built for motion. All of that is built in the very interactive 22-minute videos that we discussed with. And so we would invite you to that in May. Let's see, what else do I need to talk about? A few prayer concerns. The ICR Discovery Center was up there this past Wednesday in Dallas. In October, the Institute of Creation Research will open a $37 million creation museum in the Dallas area. It's called the ICR Discovery Center. They have it, the building is finished. Now they've got to get all the bells and whistles inside it. And again, they hope to have a grand opening by October. Alpha Mega Institute, which is great partners with us. Come on in, folks. They have a full summer of activities. You can see some of them publicized on our back table later this evening. Pray for them because they're opening up a new student center in the Grand Junction, Colorado area, and they are touching a lot of lives this summer in terms of their summer camps in Colorado. We always need sponsors for our radio programs. I'll go over our radio programs in a moment. And do also pray for the Branson Creation Experience Museum. You may not have noticed, but just outside of Branson, Missouri, is a small creation museum. They have now bought 53 acres and are planning on building a $2 million creation museum just outside of Branson. Pray for that endeavor. You will find, if you wanted hard copies of our communique back there. This month we have current events in creation science, X-Men science, which is not science, creation potpourri, just a wide variety of different things in our newsletter, and also our monthly Creationist Genesis commentary, which goes through Genesis chapter 1 about a verse at a time with great background from a creationist point of view. All of that is available in hard copy back there for free, but also it's available online on our website, and you can get our card back there so that you can view all of our 20 years of newsletters like that.
Good stuff every month.
Huh?
Good stuff every month.
I hope so. I would remind you that we're on radio every Saturday at 1:45. Let's see. This Saturday coming up is 4:27. The topic is Collision Moon. And I won't say anything more than that. You're welcome to tune in. If you can't tune in at 1:45 on a Saturday afternoon, all of our radio programs are on podcasts. And you can tune in to KSLR website, the Word to South Texas, at any time and get our radio program. All right. Let's get with the program of the evening. Dr. Daniel Harris, PhD Astronomy?
That's right.
From where?
University of Arizona.
University of Arizona.
I was the last person to finish a PhD in astronomy that covered observational, experimental, and theoretical, all in one topic.
As a graduate student, this guy got one of the rare opportunities to play with the original moon rocks as they came back.
No, I didn't.
I thought you did. Didn't you get to play with the data?
No, I just took the data off of publications.
Understood, but you took the original data from that.
Oh, yeah.
Yes. Yes.
I didn't play with moon rocks.
Okay. You got to play with moon rock data.
Okay.
This guy also chased UFOs for a while until God told him to stop doing it.
Exactly.
He's going to talk to us tonight about God's creation and the universe. And Dr. Harris, I am going to turn this over to you, and I'm going to get my program off of here.
Now, if I can get this thing to work. There we go. Yes. Okay.
You're there.
There we go. Now, when I finished my PhD in astronomy, there was a bunch of stuff that I knew that didn't make sense in terms of what they were trying to teach me. They were trying to teach me that the universe started with the Big Bang and that stars formed out of gas clouds and that the solar system formed by condensation out of a gas cloud and so on and so on and so on. But there are quite a number of things that I paid attention. I paid attention during graduate school. I paid attention. And I caught some things that really didn't line up with the conventional wisdom. And I thought that I would share some of that with you today. Okay? Bless you. In Jesus' name. Now let's see. This is the true age of the earth. Now, I'm not going to tell you a lot. I'm going to tell you the best I know. Okay? The true age of the earth. 12,021 years. Okay. The true age of the earth begins with astronomy. And the best science says, what? The earth is young. No time for evolution. I like that picture. You like that picture? The western wall. Isn't that fun? Isn't that fun? We know that the age of the earth is a pivotal question of faith. Nobody was there. None of us was there when the earth formed. We have to take it on the basis of faith. So let's look into it. As an astronomer, when I finished my PhD, there were several facts from astronomy that suggested a young earth and therefore creation. And these are some of those that we're going to talk about tonight. Comets have very short lives. That's number one. Number two, little interstellar ice. That was the thing that I did my dissertation on. I measured the ice between the stars, and it just wasn't there.
Is that because nobody else wanted to?
No, it was a miracle of God that Lord arranged for me to work with a fellow who had the capability of designing a device that would work there, and I built the device, I put it together, and it was the best infrared photometer in the world for 5 years. And that's what we used to measure the ice. And number three, stars don't condense out of interstellar gas. They don't. Now, if you have an aerosol can and there's pressure inside, and you open the valve, which way does the gas go? Out. It doesn't go in. Is there any gravitational pull that amount of gas can pull to suck that thing in? No, it doesn't happen that way. The solar system can't form from hot clouds. Well, actually, from cold gas clouds. And spiral galaxies are winding up. Spiral galaxies are winding up, therefore, the galaxies have to be young, very young, very young, very young. And number six, the supernovas going off in the galaxy should make the interstellar medium like Swiss cheese. But it's not Swiss cheese. There's only a few hundred of those supernovas that go off. And last, the Big Bang is a big mistake. I like to say the Big Bang. is a big mistake. Now, here we go. Here we are. Comets shed material when they go around the sun. Anytime they come within the orbit of Mars, they get hot enough so that they can shed material. Now, the alleged Oort cloud has never been seen. Nobody's ever seen this cloud. It's supposed to be the source of the comet. We know that there is no other source of comets. And therefore, the comets, who can only last for about 10,000 years, tell us that the solar system is young. Now, as I did my dissertation, this was the thing I used to use a photometer like that, filled up with liquid nitrogen, measured the interstellar ice. There was very little interstellar ice. Now, how can that be? There's plenty of hydrogen, there's plenty of oxygen. That should make water. Well, how come it doesn't condense? Because it hasn't had time. Because the galaxy is young. The galaxy is very young. The ice is not there. This was published in the Astrophysical Journal. Okay. Now, third thing I was going to talk about was interstellar gas clouds do not condense to make stars. In fact, you'll be surprised what we call them. Now, this is a cloud called Barnard 68. Right there. Barnard was a fellow in the early 1900s who did a catalog of dark clouds. And Barnard 68 has been recently measured to have a temperature inside of 10 degrees absolute.
It's cold.
Now that's 263 degrees below 0 Celsius, 450 degrees below 0 Fahrenheit. Now,
10 degrees Celsius, Kelvin.
12 degrees Kelvin. Now, the densest clouds have temperatures on the order of 10 to 20 Kelvin. Now, it turns out that that is enough energy to keep them from collapsing. There's enough kinetic energy there to keep them from collapsing. In fact, they have done measures of this particular cloud recently, and it says that it's at equilibrium. It said the temperature inside is at 10 Kelvin, and Barnard 68 is in static equilibrium. It's in static equilibrium. That means it's just sitting there. It's not collapsing. It's not forming stars. It's just sitting there. Why is that? Because the pressure inside is enough to keep the gravity from collapsing. No one has ever seen a gas and dust cloud collapse to make stars. Now, this is the famous picture that everybody talks about. They say, "Oh, this is the stuff collapsing." No, what's actually happening here is that there are some stars off the top out of the view that are shining hot like high energy radiation and streaming gas on these things, and they are eroding away the dust cloud. So this is a dust cloud that is being eaten away. It said these stars are sending UV light and stellar winds to burn up and blow away the dust, leaving only the densest clouds. This is not star formation. This is dust cloud being blown away. Now, astronomers have assumed that stars condense out of dust clouds. But recent observations have shown that stars are emitting gas. Okay? They're rejecting gas. They're throwing off gas. Now, they can lose half of their mass before they become giant stars. And the mass loss rate is quite considerable. 10 to the minus 4 solar masses per year. Now, If you have 10 to the 4 years, which is 10,000 years, how much of a mass do you get? One solar mass. Each one of the stars can reject one solar mass in 10,000 years. So, it is reasonable to suppose it could be that the stars are making the clouds. It's not the clouds that are making the stars. Isn't that fun? Isn't that fun? I think that's really fun. It's the stars that are making the clouds, not the clouds that are making the stars. Now, the next thing we want to talk about is the formation of the solar system. And the typical thing that they say about that is that a gas and dust cloud collapsed, formed the sun and a disk of rotating gas and dust, and out of that formed the solar system. This is the astronomer's fairy tale, and it is a fairy tale. Okay? Now, why is it a fairy tale? Well, there's a serious problem with this standard idea. There is a serious problem with this. As dust grains grow by colliding with each other and sticking, that's when the temperature in the cloud is hot. They stick to each other when the cloud is hot. But what happens is that the number of dust grains drops. They coalesce. They coalesce. As they coalesce, what happens? The number of grains is less. If the number of grains is less, then the heat from the cloud escapes. The heat leaves. The heat leaves. When the heat leaves, what happens? These particles, these grains, these clumps, become cooler. They get below a temperature where they are brittle. So what happens? When they collide with each other, instead of growing by sticking together, suddenly they're colliding with each other and shattering and making smaller things instead of bigger things. Very interesting. The rock grains become brittle and fracture in collisions, stopping the growth. And what do you get? Before the rocks can grow big, you wind up with things that are the size of basketball or football. That's as big as it gets. The particles do not grow anymore. The best models say that we get a basketball-sized object is the largest stuff that you get. That's not enough for gravity to condense these particles into planets. Now, this is a thing that I got off the net showing collisions. Yeah, the collisions are occurring. Collisions shatter the stuff. Instead of the particles growing, they shatter. Okay. Collisions and fracturing stop planetesimal growth. The best computer simulation shows that no planets form. No planets form. What you get is a uniform disk of small rocks. And that's what we see around other stars. We see lots of disks of dust, this kind of stuff, around other stars. Okay? The rings of the outer planets, and there's plenty of rings out there. There's Saturn's ring, Jupiter has a ring, Uranus has a ring, Neptune has a ring. They all have rings. The rings of the outer planets show that rocks and ice rings are stable. They don't gravitationally collapse into big objects. If the rings of the outer planets do not collapse into things that are bigger, then it is reasonable to suppose that those things that we see around other stars do the same. Yeah, they don't collapse and form new stars. They don't do that. They don't form planets. They don't form anything. They stay pretty much the way they are. So, the rocks and the ice and the rings are stable. There is no naturalistic model for the early solar system, how the solar system can come to be. So the solar system cannot be created by any of the mechanisms that have been proposed by naturalistic astronomers. And I knew this when I finished my PhD. But I was still an astronomer. Now, this is the next big section of this thing. Many galaxies are beautiful spirals. And these are beautiful. In them, gas and dust, clouds, and hot blue stars are arranged along spiral arms. Now, our sun is inside a galaxy like that, the Milky Way, and these days they think that the Milky Way is this barred spiral with a bar in the middle. This is the artist's view, and the sun is at the bottom, about right there. Now, this is a view of the Milky Way, and from, as we see it, inside, looking towards the center. This is a wide field view of the Milky Way centered on the galactic center. Now, the center is pointed exactly at the point, right there. That's exactly the center. Note the flattened disk shape. It's a disk flattened. Okay. There are no heavy. Note also that there are heavy bands of obscuring dust. Now this is where we are towards the edge of the galaxy. This is an artist's view. Obviously, nobody's been there to take a picture. Okay. There is a serious problem with the measured rotation of spiral galaxies, which implies that over time the spiral arms should be winding up. Now, if you have a disk, a solid disk, rotating, and you put little dots on it, they will go around and they will just stay in the same relationship. So a solid disk preserves the spiral, any pattern you put on it. A solid disk rotation will do that. Now you notice that near the center of the rotation, the distance you move is less. Farther out you go more. So the distance that you are out is proportional to the speed. Speed is proportional to the distance. So that'll give you a preservation of spiral arms. They will not wind up. Now, if you have planetary motion, like a strong simple mass, and like Mercury and Venus and so on, that'll spin up very quickly. That will wind up very, very fast. Now, this is how we measure these galaxy rotations. We use the light from the galaxy, the light that is coming from in this direction towards us, from the stuff that's approaching, is blue shifted. The light that is moving from the gas that's moving away from us is red shifted. The approaching side has a blue shift, the receding side has a red shift, and that is how we measure the rotation of galaxies. Now this is this is the rotation curve, as they call it, of the galaxy. And this is, along the bottom, is distance from the center. This is bigger distance out, big distance here, small distance there. This is the small rotation speed. This is higher speed. Notice that right near the center, this is almost a straight line. That's almost solid disk rotation right there. So that near the center, you get almost solid disk rotation. But out far away, there's almost constant speed. This is the galaxy right there. That's a picture of the one that's in the red light. There are, for most spirals, 3 regions for the rotation. The inner region, which has a straight line, is very much like a solid wheel. Then there's a transition zone, and then there's a region for the outer portion, which has a constant speed of rotation. Constant speed of rotation. Okay? And here we are. See, the distance from up is constant. It's constant speed. This is almost flat, almost flat. The speed here is about the same as the speed there. Okay, but near the center, this is almost a straight line curve. The straight line curve means that the thing is behaving like a solid disk. Now, this is our galaxy, the Milky Way. And it has a variation up and down from the middle of about 10%. 10% variation is all it does. And this is the speed of our galaxy. The speed is 240 kilometers per second at the distance we are. So it's only varying by about 10%. Now this is going to be a key idea for you to think about. Now, this is an inner track, and that outer track is 4 times farther. It's 4 times farther out, so it's got 4 times farther to go around. 4 times farther around than the one in the middle. Okay, got it? This one track has got a radius of 1, and this track has a radius of 4. Got it? Okay. Now, they all are moving at the same speed, just like the diagram showed. All moving at the same speed because that's part of the diagram. So they're all moving at the same speed. Near the center and the outer edge, they're four times the distance from the center, but it's at the same speed. Now, what happens after half of a turn for the inner material? The inner material goes half a turn. The outer goes 1/8 of a turn. And so you get this little bit of a curve. So you have a half of a turn for the curve, half of a turn there, and 1/8 of a turn there. After the center has gone around one complete orbit, the outer one has only gone 1/4 of an orbit, and so this is what it looks like. See how it's winding up? It's winding up. Now, so this has only gone 1/4 of a turn. This has gone 1 whole turn because that thing out there is 4 times farther. That's got 4 times farther to go because the circumference is 4 times bigger. Now, okay, in this diagram you see the starting lineup, how they was with the half and time 2 and then time 3. So you see how they wind up. Stars on the inner track do 1 full orbit, while 4 times farther out, you do 1/4 of a turn. The arms should be winding up. Now, our galaxy's inner quarter should quickly gain on the outer region, winding up the spiral arms, just like it shows here. The arms should wind up. Okay? Why is it not advancing?
While you're playing with that, Dr. Harris, the point you're making, if I catch it, is that because of the motions we observe in these galaxies, they should be like that final thing on the right. If they're billions of years old, they all should be
wound up.
But that's not what we see.
That's not what we see, and we're going to look at a bunch of galaxies right now. But real galaxies are not wound up. Real spiral galaxies have nearly constant arm angle center to edge. Now, this is M51, a very famous spiral. Now notice that the spiral angle is about the same as you notice the angle there, and notice the angle there, it's about the same. The angle there is about the same. These all have about the same angle. The same angle. Doesn't matter where you are in the galaxy. Now, here's the inner portion of the same galaxy, and again, you see the same thing. You've got the same angle there, the same angle there, the same angle there. Fascinating. Now, this looks like the wonderful spiral that God has designed into so many different things, like aloe vera, the nautilus, sunflower seed, sunflower, and the cyclone. All these things have the same kind of pattern. Isn't it fascinating? It's fascinating that the Lord has designed these things to look beautiful. They look beautiful. That's why they look that way. Now, this is the galaxy M1 also showing almost uniform angle. See, the angle is the same there, angle same there, angle same there, angle same there. Isn't that fascinating? Now, this is another one that does the same thing. NGC 3370. Constant arm angle. Now, this one is a barred spiral, and it can't wind up. So it's not wound up. Here's another one. It's constant angle. Now here's another one. Are you getting the pattern? Yeah. They don't look like they're winding up, do they? Now, the time for the sun to orbit the galaxy is about 210 million years. And it's clear from the pattern that we see in the galaxy that the Milky Way shows that it is not rotated probably much at all, less than 1/15 of one rotation. So take 210 million years and divide by 15. What do you get? You get 14 million years. So that's the maximum age of the galaxy, folks, from rotation of the galaxy. This is the measured rotation of the galaxy, shows that it has to be less than 14 million years. No time for evolution to happen. Okay? The galaxy is young. Galactic rotation gives us a crude upper limit on the age of galaxies. Clearly, spiral galaxies could be much younger. Now, these are supernovas. Supernovas go off, bang! Get your attention.
I won't.
Yes.
We now consider the problem of the missing supernova remnants. The supernovas go off periodically in the galaxy, and they make a hole in the interstellar material. And there is one. That's what they call a GIF. It recycles. That's a supernova going off. Okay. A hot gas shell expands and ejects one mass of the sun moving at over 7,000 kilometers per second. Now, what is that? That is a speed of 4,000 miles per second, which is about 20,000 times faster than a speeding bullet. You think Superman's fast? This is much faster. Okay. So supernova does this, and it throws the shell gas off into the interstellar space, and it should make a hole, which is why the interstellar dust and gas should be a Swiss cheese. Now, the supernova can briefly outshine the entire galaxy. That one star can briefly, not for very long, but it can briefly outshine the entire galaxy. This is one in our familiar friend M51 again. M51 had a supernova right there. Now, supernovas are occurring all the time. These are the most recent ones. In fact, I downloaded that image just this afternoon. This one right here. This one I downloaded this afternoon. This was the latest image of a decent looking supernova that I could find, 2017, September. Before that, we had September of 2016, we had one right there. Now, recent supernova in January of 2014 was in the M82, right there. And then there's two supernovas that occur in NGC 2770, two within a very short time of each other. They're going off all the time. Now, this is the Crab Nebula. It's a supernova gas shell that went off in 1054 AD, and Chinese astronomers saw it. It's at a distance of 6,500 years, so this is close. If they get much closer than this, we're in danger. Now this is what it looks like with a radio telescope. Notice that with a radio telescope, it's very easy to see against the background because it's very bright. See, the background is dark. This thing is very bright, bright, dark, bright, bright, dark, bright, dark. Okay. So this is very bright against the background. This is the supernova that was seen by Kepler in 1604. And it's bright in all colors, X-rays, visible, and infrared. Visible is not quite as obvious in the invisible. This remnant is very bright, all of the way from X-rays into the infrared. It's easy to see against the background. Now this is what it looks like with a radio telescope. Again, it's bright against the background. And we can see this all the way through the interstellar dust. Now this is a supernova that went off in 1572 that Tycho saw. Now that's not a train, folks, that's an astronomer. Okay. This is an X-ray image of the supernova from 1572. Now this is an image of it in the radio telescope. Notice again, it's very bright against the background. Now because we are inside of a disk of dust and gas, we can't see very far because of the dust. But with a radio telescope, we can see all the way across the galaxy. You can see only the local galactic neighborhood with light. But with a radio telescope, you can see the whole galaxy. So you need a radio telescope in order to do this.